an old exponent rule. If you have b to the power of m to the power of n, can you tell me in Google Chat what that is? I'm looking in Google Chat. Yes. So I'm going to write it in here. You multiply the exponents. So now let me emphasize. There is an operation outside, and you are exponentiating. Unfortunately, someone did not come up with a good word to use for this. So exponentiation. So basically putting something to a power of something. Yeah, you can put it on a separate sheet of paper. Okay, then the operation that is inside is multiplication. And as before, remember that inverse functions swap. What do they swap? X and Y, which means, that the one function's input inside the function swaps with its inverse function's output outside the function. So now, I want to say again, you have an exponent outside of the function. So now what we're going to do is we're going to write a logarithm. Log base b of, I can't remember which letters I used. It's just going to bug me if I don't use the same letters. I used X and P. Okay. So if I have log base b of X, and I want to look at exponentiating instead of outside the function, exponentiating inside the function, then inside this parentheses, I'm going to put a power, P for power. Now, I don't have to have that parentheses, and that's the notation note. And now what I'm going to do is I'm going to write log base b of X. Now, multiplication was the operation that was inside the exponentials. So now I'm going to have outside multiplication by that power. This is the third of the big three log rules that you will be using. And actually, you have all the log rules you need to know at this point, because we have looked at the inverse properties, and I will be mentioning these again, but together with those inverse properties, you only need these big three rules. So notation note, just to make sure you're clear, I do not have to write a parentheses to mean the same thing, but they probably should have had that done. Okay, here we go. Expanding. We're going to go a step further with expanding. First, you should see that you have multiplication between 3 and a to the 5th power. So you have log base 8 of 3 plus log base 8 of a to the 5th power, going back to that sum rule that we learned last week. With the new rule, I can take this exponent and turn it into multiplication in front of the logarithm. So now when I expand it, it's log base 8 of 3 plus 5 times log base 8 of a, and that would be considered expanded. The multiplication, you want to put it in front because if you don't, it might be considered to be inside when it should be outside. Things that you can do, you can write it this way, and then it's clear that the 5 is multiplied to the logarithm. But without that extra parentheses, it's not clear. So that's why we usually put the multiplication in front. All right, next problem, number 2. Can you put it in front? Oh, you cannot put it in front of this logarithm. That exponent is only for the a, it is not for the 3. So only the logarithm that has a inside of it gets to have the multiplication by 5. For number 2, you want to see that you have division. So this turns into log base 5 of, and does everyone remember the subtraction rule? Now, I'm not going to do this, what I'm about to say, I'm not going to do it to you in the middle of a quiz or test. Alec, you need to mute your mic. Thank you. What they have you doing is factoring x squared minus 25 into x. Does everyone see how it factors? So it's x plus 5 times x minus 5 in that logarithm. And right now I'm just making one change at a time. And I'm about to kill my neighbor. No, I don't. Strike that. I don't mean that. I just realized I'm taping myself too. But not only were they jackhammering, now I can literally feel them beating. I don't know what they're doing, but I can feel it vibrating the house. I'm so thrilled. Okay. Now, this multiplication, I'm not going to ask this much of you. Again, I'm not going to ask this much of you on a quiz or a test. They expect you to see that you can factor that quadratic and turn it into this addition. But also, this x squared can have the 2 brought in front. That 2 can only be with the x because only the x had that exponent. But also part of showing you this is to show you that you've got an x squared here and you've got an x squared here. For this x squared at the bottom, it didn't have anything added or subtracted to it, so that exponent was able to come out and multiply. But in the numerator, you need to see that this subtraction right here that goes with that x squared means that that squared cannot come out on its own. The only thing you can do, if it's possible, is factor it and take individual factors and separate that with addition in a logarithm. Okay. Then for this third one with expanding, there's no base written, so we understand it to be what base? What base do we understand it to be? 10. Good. So with number 3, that means I just don't have to write a base. So I have 1000t minus, and then I have q to the 5th, okay, q to the 5th power times the square root of r. Now, there's more. And this is now that you have all three rules, you're going to get a whole bunch of, but wait, there's more. There is multiplication going on within each of these logarithms. So to continue expanding, I now have log of 1,000 plus log of t. With this subtraction, I need to be very, very, very careful. I'm going to separate the multiplication, and I can do one of two things. I can either put minus and then a parentheses, or I can distribute while I'm in the middle of a log rule, which I would advise against. But if you can do it right, that's fine. So log of q to the 5th power plus log of the square root of r. Now, let's start with the log of 1,000. Does that simplify to a nice, pretty integer? What integer is that? Good, 3. So I have 3 plus log t. Now, I'm going to clarify, and this negative sign is distributing through. And I did that right there to make sure that was clear. Now, this q to the 5th power, the exponent 5 is allowed to multiply in front of that logarithm. And do you remember the exponent that a square root is actually representing? What is the exponent that a square root is? Yep, 1/2. So that means that you can look at this as r to the 1/2 power inside your logarithm. The 1/2 can come out and multiply to that logarithm. And then this would be considered expanded. And next I'm going into condensing. Condense is nice because you know when you're done. As you go through condensing, you need to first look for multiplication. Deal with the multiplication before you deal with the addition subtraction as far as condensing. So the new rule today is that 6 can become an exponent inside that logarithm, and now that 6 is not there anymore. And I'm going to do one step at a time. As I add these two logarithms, I can turn that into multiplication inside one logarithm. And then with subtraction, I can continue to bring that into one logarithm. And what operation am I going to have inside? You can say it in chat. What? Or say it out loud. Division. Now, at this point, if you decide you're going to multiply those two binomials. If you decide you're going to multiply them, you can. If you decide you're not going to, you can also. This just asks you to condense. Condense means everything winds up inside that logarithm. Everything is now inside the logarithm. That is good enough. You can stop there. And then one more example. Okay, one more example. Of course, got to make it harder, huh? Now, 5 is a constant multiple, but 3 is all on its own. If I have a number multiplied outside a logarithm, I can quickly bring it in. But the lonesome 3, I have to use the inverse property. So I need to turn 3 into a log base 2 logarithm. And whatever is inside there is going to be inside there. But that expression needs to be equal to 3. If that expression is going to equal 3, I need to have the exact inverse of log base 2, and that would be 2 to the power of, and then where you would put the x, that's where you need to have the number that you're trying to turn into a logarithm. So take a good look. The inverse property says 3 goes into the exponential function with base 2. That result then goes into log base 2, which takes you right back to where you started with the 3. I'm going to erase the equals 3 part. And then move to the next step, understanding that this is now what I'm using instead of the 3. I've got addition. So with that addition, I can make that one logarithm with multiplication inside. And you know, both of these are subtracting. So if I want to, I could go minus parentheses. And then I have inside 2 to the 3rd power times inside x to the 5th power. And I just realized I didn't write my logarithm. That was silly. So again, I distributed out, let me erase a little bit here to clarify. This negative sign I distributed out here so that now I'm dealing with this situation, but that 3 is log base 2 of 2 to the 3rd power. And I had already changed that other one, didn't I? And so I'm using the rule of when I'm adding logarithms, I multiply their insides. This subtraction sign says I can turn this into a division between the two. So log base 2 of, and this lovely numerator. It's an issue of the distribution of that negative sign. And I'm going to go right back to it in a second. Let me finish writing this down, and then I'll go back to that issue. So this would be considered a condensed logarithm. However, what is 2 to the 3rd power? What is 2 to the 3rd power? 8. So I want to say the directions only said condense. So that means you can leave it as 2 to the 3rd power, or you can write it as an 8. Now, I need to go back. I'm going to erase everything except the answer, because I want to clarify that issue with the subtraction, because it's just one of those really annoying issues that get in the way. So this entire piece was rewritten as subtracting log base 2 of 2 to the 3rd power and subtracting 5 log base 2 of x. What's very, very important for you to notice is this subtraction that came from here. Because that is being subtracted, I can't just use that division rule, because the division rule is based on a positive logarithm minus a logarithm. And I need to bring that 5 over here. So if this is what I saw, then I could say this is log base 2 of 2 cubed divided by x. But this extra negative sign, if I'm going to even bother doing division, I actually need to make that a positive before I can do that, which you honestly don't want to do. So what I recommend you do is take every term that is subtracting, take every single term that is subtracting and group them together. And then put a big subtraction of minus all of them and then write them as addition. And then you can use the rule of when you're adding, those multiply. I know. And this is why I gave you a couple of rules to think on and get acquainted with before throwing the whole thing at you. And do you see why now I have so many review days scheduled? Yeah, that's really, really normal to feel confused right now. Very, very normal. You are having to now fully adjust to doing arithmetic rules with logarithms, which is very confusing because logarithms are exponents. So you're throwing arithmetic rules onto exponents. And to do that, you've got to use the exponent rules you already know. It's not easy. This is why people say logarithms are difficult. This is why they don't like them. And I will keep going over this with you. Do you want me to literally take you through the whole thing again? Yes. Oh, I had erased what I did, but this piece right here, I used the new rule we learned today, and that multiplication of 5 turned into an exponent of the 5. And that doesn't feel normal. It's not normal. Okay. So I'm guessing that right about now, a short break from logarithms sounds good, right? That's why I threw this in there. I had saved a couple of graphs for now. So let's get off logarithms for a minute, shake it out of your head. And we are literally going to need to talk about what we just did all week long. Every single day I need to sit here and talk you through more of these problems. And it'll get better. It just takes time. Okay. So, logarithms gone. Woohoo! Who's happy? Out with the logs. Okay. So, no, they can't be gone for good. I'm sorry. What is the inverse of cube root of x? Anyone remember what the inverse is for cube root of x? X to the third power. And actually, you're going to be quizzing on your knowledge of the graph of x cubed today. So this is going to be very important. And anytime you deal with a function that is an inverse of somebody we're familiar with, you kind of want to work backward. So you know what? I'll write it to the side. Cube root of x. If the cube root of x is equal to -3, what was the x? So what number do I take the cube root of and I get -3? There you go, -27. And one thing you can do is you can third power both sides. And -3 multiplied 3 times. If you have to, you can write it all out, but we get -27. Now I'm going to move on to the next one. If the cube root of x is equal to -2, then what is x? -8. Good. If the cube root of x is equal to -1, that was poorly drawn. What is x if its cube root is going to give you -1? -1, good. Next, if the cube root of x equals 0, what is x? Good. And you guys think you can get these last three pretty quickly. I know. I'm frying brains. Yes, 1/827. This is why I did not feel it was a good idea to give you this test this week. You actually need at least a good solid week once you have gotten all the log rules to process them. All right, now here we go. You are going to sketch the graph of y equals x cubed. Do you remember what it looks like? Because you are quizzing on it today. I'm going to draw y equals x cubed in blue. You should remember that it goes through 0, 0, 1, 1, -1, -1, and 2, 8, -2, -8. Do you remember it's flat in the middle? I can redraw that in black. Again, x cubed is flat in the middle. You will be quizzing on it today. Trying to go through that point. Now, if you draw the line y equals x, you can reflect this over that line and you will see the x cubed or the cube root of x graph. So just think of 2 to the x and you'll be good. Alec, no. No, 2 to the x is a very different graph. I'm going to show you the answer because it's much easier to read than my drawing. Okay. is it? There we go. In blue, you can see the graph of y equals x cubed. And then I have a dashed line for y equals x. And then in red, you can see the cube root. And if you're having trouble seeing the different colors, let me grab a Desmos and show you what it should look like. And I can change the colors on here quickly. So I'm going to change the colors on both of these graphs then. Do you see how pretty they look together? And I'm also going to do this. So isn't that pretty? That's both of them together. Now, I'm going to take off, we're going to look again at x cubed, which again, that is in your quiz today. Now I'm going to deselect it and we're going to look at the cube root of x by itself. It's a very interesting graph. It becomes vertically steep here in the middle, but only at that one point is it actually vertically steep. Otherwise, it's just extraordinarily steep. So this is the cube root of x. This is your new graph that you want to become familiar with. And I'm going to ask you to always plot 3 points. Those 3 points are 0, 0, 1, 1, and -1, -1. Those are a very important trio. So if it is cubed, it is this way, but if it's cube rooted, it is that way. Yeah. Yeah. So it's a sideways x cubed, which you would expect. And then for practice, I need to write the domain, range, and inflection point. You ready for some free points? Free points are if I ask you domain and range, because all real numbers go in, all real numbers come out. You can plot those 3 points, 0, 0, 1, 1, -1, -1, but then you need to, x cubed goes through the same trio, but x cubed is like, whoa, while cube root is like, whee, if that helps. But both x cubed and cube root have a domain and range of everything. The inflection point is the center of the graph, 0, 0. So can you draw these 3 graphs? And I'm going to show the answers to that because I'm running out of time, unfortunately. Now, I also have plotted the points 8, 2 and -8, -2. I expect as a minimum, though, that you plot this inner trio. The next graph, you're multiplying by 3, so that's vertically stretching. And you can see the x-coordinates, 1 and -1, just have their y-coordinates multiplied by 3. And also at 8 and -8, the y coordinates of 2, -2 were multiplied by 3 to get 6 and -6. And then in part C, you are moving the graph. What does this -2 inside cause? -2 inside, yes, moves it right 2. And then -4 outside moves it 4 down. And so you can see following this trio of points is a minimum of what I'm asking you to do, but you need to draw to the edge of the grid. I'm allowing you to be slightly inaccurate as you move away from these 3 points and not be perfect, but make sure that you have the graph. It should not look like x cubed looks. So x cubed curves up like this way. Don't let it do that. One thing you can think of as what I'm expecting, do you see that from the inflection point here, do you see that this is kind of a frown, a sad face? It's someone going, meh, meh. But this half over here looks like half of a smile. And that's what an inflection point is it's a change in the graph curving like a smile to curving to a frown one way or the other way. Okay, I need to get you going on that quiz. Before I do, let me remind you that the only thing you have for 3-3 is the rule for addition, where you're adding 2 logarithms, so it becomes multiplication inside. And that goes with expanding and condensing. Then the graph of x cubed, I've got a multiple choice for that one. I'm going to stop